Alright, so we've defined additive function and countably additive function in the last video, and like I said, now we want to look at some equivalent conditions to countably additive. So this time we're going to start with an algebra of sets on X. This is proposition 133. So assume you have an algebra of sets on X. And might sound weird at first to talk about countably additive for something that is an algebra of sets and not a sigma algebra. But again, we want to use this in a context where we're extending functions mu from less good collections of sets like algebras to good, better ones like sigma algebras. So for that context, we need the language of countably additive even while this is not a sigma algebra. So assume it's an algebra. Assume mu is additive. So this whole thing, we're assuming mu is additive, and we're going to look at, under the assumption that mu is known to be additive, some equivalent conditions to countably additive. So there's these two. One of them is mu is, quote, continuous at the empty set, and the other is mu is, quote, continuous from below. So these are not defined terminologies, so there's a colon here saying that I'm about to elaborate on what I mean by this. So continuous at the empty set. So in analysis, when you say a function is continuous, like when you say f continuous at, so this is unrelated to this stuff, just in general, if you say f is continuous at, say, x naught, then one way to describe this is to say whenever you have a sequence converging to x naught, applying f to the terms of the sequence converges to f of x naught, right? Assuming you can apply f to the terms or whatever. So this is a way of expressing continuity. A function is continuous at a point when the function preserves convergence of sequences to that point, right? So this phrase in quotes here is sort of following this pattern. Mu, if you have a sequence of, so the domain of mu here is not the reals, right? And it's not even a metric space. It's a collection of subsets of x. So I'm not going to talk about convergence, but there's convergence in the set theoretic sense, kind of, not the calculus sense, like this. So whenever you have a sequence in the domain of mu, is a sequence of elements of this algebra of sets that, quote, converges to the empty set. This is what we're going to mean by converges to the empty set. So it's a nested sequence with all of the sets sort of shrinking, and the intersection of all of them is empty. Then we have, if you apply mu to these sets, then that sequence of real numbers converges to 0 in the calculus real analysis sense. And remember, 0 is the mu of the empty set, right? We're talking about an algebra of sets here, so the empty set is definitely in the collection fancy A. So there is such a thing as mu of the empty set. And as we discussed in the previous video, since mu is additive, mu of the empty set will be 0. So you can look at this as mu preserving limits. If you think of this as kind of like a limit, and then you apply mu to everything, the mu of these converges to the mu of this, which is 0. And then this continuous from below thing is a similar idea, but it's about families of sets that build up rather than building down to something. So whenever AN is a sequence of things in A, in fancy A, and they build up to this set, let's call it A, and now I'm going to start talking about the mu of the ANs, which is fine, but I also need to talk about the mu of the A, right? Which A is good. This statement here says that A is the union of all the ANs, right? That might not be in fancy A. We didn't have that problem up here since we were talking about the empty set, and that's in fancy A. The empty set is always in any algebra of sets, but it's an algebra of sets. It need not be closed under countable unions. So I need to add the assumption here that the quote limit, or the union, of the ANs is actually in there. So whenever I have a sequence like that building up to something that is also in the algebra of sets, we have the limit is preserved in this sense. So mu of the ANs converges as a sequence of real numbers, converges to mu of A. All right, so that's continuous from below. So if this one was like continuous at the empty set, then maybe you can call it continuous at the empty set from above. And this one you could call continuous at every point set A here, but from below. And these are equivalent. These two are equivalent, and equivalent to saying mu is countably additive. And pretty soon we're going to define the word measure officially, and to say that mu is countably additive is to say that mu is a measure on the on this. I guess I shouldn't call it a measurable space since A is not necessarily a sigma algebra here, but on this almost measurable space object thing. So these are equivalent conditions to having an additive function qualify to be a measure. Okay, measure not defined yet, that's coming up very soon. All right, so I'm going to prove 1 implies 2, 2 implies 3, 3 implies 1. And we'll start with 1 implies 2 here. Okay, so I'm just going to copy over some stuff off screen. All right, so here I've copied everything over. Let A be an algebra of sets on X, and let mu be an additive function. And now assume further that mu is countably additive. So above this line is just the global assumptions in the theorem as a whole, and then this is assuming number 1. Now we need to prove number 2, so we need to prove continuous at empty set. So let AN be a sequence in A which goes down towards the empty set. So that means they're nested and their intersection is the empty set. So what I know about mu is that it's countably additive. That tells me something about what happens when I have a sequence of disjoint sets. It tells me about mu of the union versus the series of the mu's, right? So my problem here is that I cannot apply mu, that idea of countable additivity directly to this, right? These are not pairwise disjoint, these ANs. So right now, maybe A1, they're nested actually, right? It's almost the opposite of being pairwise disjoint. I have A1 and then A2 inside, and then A3 inside there, and so on. And if you intersect all of them, you get the empty set. So to replace them by a sequence of pairwise disjoint elements of fancy A, what I can do is focus first on this complement, just this part, and then focus on this complement, and so on. And I'm going to call these B1, B2, etc. So let B sub n equal A sub n plus 1, delete, they're nested in such a way that this is the kind of deletion I want to make. A sub n, delete A sub n plus 1. So B1 is A1, delete A2. B2 is A2, delete A3, and so on. Now, again, I want to apply countable additivity of mu. So now I wanted a collection of disjoint sets. Hopefully Bn is that. So then the Bn are pairwise disjoint. So that's a claim that I should verify. And the union of the Bn's is the same as the union of the ANs. It's just less redundant as you take the union. And the union of the ANs, since the ANs are down arrowing their way to the empty set, they're nested in such a way that, you know, they're all subsets of A1. So when you union all of them, you just get A1, right? So the reason I'm saying this is that in order to apply the countable additivity of mu to the sequence Bn, I need both that the Pn be pairwise disjoint, which I'm about to verify in a moment, but I also need that their union is in fancy A. So observing that the union is A1 is a way to see that it is in fancy A. Right? Like if you look back to the definition of countably additive, you need the union to be in fancy A. That's not guaranteed. Here A is merely an algebra of sets, not necessarily a sigma algebra. Okay, let's quickly think about pairwise disjoint. Probably it seems obvious from the picture, right, that those deletions that I was making would make the sets disjoint. But let's just do a quick check. So if I take, let's say, Bn and Bm and think about their intersection, that would be An, delete An plus 1, intersect Am, delete Am plus 1, right? Now let's imagine that N and M are not equal. Then we want to show that this is empty. This intersection is empty. That's what pairwise disjoint means, right? So then without loss of generality, one of them is smaller. Let's say N is smaller than M. So let's see, these sets are shrinking. So as I increase the index from N to M, the later set A sub M is included in the earlier set A sub N, right? That's the sort of nesting that's contained in the down arrow information here. And the same is true if I look at M plus 1 and N plus 1 here, which I think is where I want to look. And, you know, this is a subset of AN due to the nesting. So if you look at this intersection here, it contains only things that are in A sub N. Sorry, no. I think this is not actually the helpful thing to look at, but something similar. Okay, let's go back to A sub M is contained in A sub N. And actually, okay, so these are integers. So if M is greater than N, M is greater than or equal to N plus 1, right? So A sub M is actually contained in A sub N plus 1. Now focus on this. Can we show this is empty? Well, all the elements of this have to be both elements of A sub M and not elements of A sub N plus 1, right? But that's impossible. Every element of A sub M is an element of A sub N plus 1. So this intersection is empty. Okay, so what the picture was showing intuitively is actually true. So the B sub N's really are pairwise disjoint, and their union is this union. That's quite an assertion, right? Let's verify this one. So is this union really the same as if I took the union A sub N delete A sub N plus 1? Is this really the same as this? Well, one inclusion is immediate and is just a general thing, and that's this one. I would say that inclusion is immediate because the things that I'm unioning here, this is always a subset of this, right? So that inclusion, there's no doubt, but this inclusion, there is definitely doubt. Somehow this is going to be something that's working out because of the way the ANs are nested, right? So let's verify. Let's suppose you've got some like point X in here. Then can I show, so that means X is in at least one of the A sub N's. can I show that x is then in at least one of these complements here? Well, focus on, I guess, the smallest index n such that x is in a sub n. So if x is in there, then x is in a sub n for some n, but choose n minimal. So sort of focus on in your nesting, focus on the first one of those sets that the first one or the last one? Hang on. Okay, so if n is minimal, then n is just going to be 1. Of course, this is totally unhelpful. Right, the smallest n such that x is in there is n equals 1, because this union is actually a1. I'm saying x is in a1. So maybe I would be helped by a little bit of a picture here. We've kind of got this point x, right? And then we've got a1, a2, a3, a4, and then maybe a5 excludes x. So there's like a maximal index that includes x. So x is in an with some n maximal. Okay, saying n minimal among a set of natural numbers is fine, but maximal? Hang on, why would that exist? Like, couldn't x just be in all of the a sub n's, in fact? No, it couldn't, because they're going down towards the empty set, right? The intersection of all of them is the empty set. So since they intersect to give the empty set, x cannot be in all of them. So that means there's a first one that x is not in. So maybe a better way to phrase this is choose n so that x is not in an, and n minimal with respect to this property that x is not in it. Yeah, that's better. So there's a first one, like in this picture, I've got a1, a2, a3, a4, a5. A5, 5 is the first one that excludes x. So there is at least one n for which this is true, because these are going down to the empty set, so x cannot be in the intersection. And so we can take the minimal n, and since n is minimal, if I go and look at n minus 1, then x is going to be in there, right? Because that's less than the minimal thing, such that x is not in there. And n minus 1 is a valid index here, because n here cannot be 1. N cannot be 1 because I already know x is in a1. All right, well then, you see, x is in a sub n minus 1, delete an, right? Which is one of the things showing up in this union here. Okay. So that was interesting. So that worked out basically because the intersection of these sets is the empty set. And the blue thing that I wrote here is just this union of the bn's. All right, and now finally I can apply countable additivity of mu, except I just realized I also need to know that the bn's themselves are in fancy A, right? So also, by the way, each bn is in fancy A. I need that because I'm going to apply the mu to the bn's. So I need, right, if you look at the definition of countable additivity, you need to be focusing on a sequence of things in fancy A. So why are the bn's in fancy A? Well, they're this complement of two things. The two things getting involved are in fancy A, and fancy A is an algebra of sets. So that's because it's an algebra of sets. Okay, now we can apply countable additivity of mu, thanks to this, the fact that the countable union is in there, each of them is in there, the countable union is in there, and they're pairwise disjoint. So let me connect this up. Thanks to these three green underlined things, we can apply countable additivity of mu. So by 1 was our assumption that mu is countably additive. the mu of the union of the bn's is the sum, or the series, infinite series, of the mu of the bn's. So remember that in here we've got also a statement that the series converges, right? This is a convergent series. So that means the terms of the series have to go to 0, right? A series can only converge when its terms go to 0. The sequence of terms have to go to 0. So that seems promising, because what I'm trying to prove, number 2 here, the thing that I'm trying to prove is that mu of the an's goes to 0, right? And I already know now, since the series converges, that the mu of the bn's goes to 0. But it's not exactly what I want, right? I want mu of the an's. So a bit more work is needed. One thing we can do is, so right here, this tells us about mu of a1, right? Like, that union in there, that's a1. And we can make this tell us about mu of a sub any given n if we just, start our union here rather than from n equals 1, from a little later along, and then let the series run from a little bit later along. So let's just verify that works, that we can apply countable additivity in that way. So now if we take only, let's start it from some capital N. So let's let capital N be a natural number. And then now if we take only b sub capital N plus 1, etc. So leaving out b1 up through b capital N, then this collection, the b sub capital N's, where the b sub little n's, where little n is taken to be greater than or equal to capital N. I guess what I'm leaving out here goes up to n minus 1, right? Then this is a sequence in there, right? Because we've already established that all of these b sub n's are in our algebra of sets. And what else do we need? They're pairwise disjoint. The sets in there are pairwise disjoint because the full collection was, so any subcollection is going to have that feature. And what about the union? So I need, in order to apply countable additivity to just this collection, I need to know that the union of these guys is an element of my algebra of sets. But the union is the same as the union of the ANs, and the proof of that fact is the same as our proof of this that we went through just now. It's the same idea, just starting later down the line. And this is, since these are nested, this is just a sub capital N, right? All of the things being unioned here are subsets of a sub capital N, and a sub capital N is one of the items in the union. So, and that's in there. So this countable union is in our algebra of sets. So we can apply countable additivity. So we can apply our assumption 1, countable additivity, in this more general setting to get mu of an for this arbitrary natural number n that we fixed is mu of this union, in other words. And countable additivity tells us that that's this series, mu of the bn's. starting from capital N onward. So still an infinite series. But see what we've shown? Mu of the ANs is this. This is the tail end of a series that we have seen converges, right? This series here converges, and this is its tail end. The tail ends of a convergent series are going to converge to 0, right? That's like what it means for a series to converge. So, I mean, actually, I guess the way we technically define it is a series converges when its sequence of partial sums converges. But what are the partial sums? What does it mean to say the sequence of partial sums converge? You look at the difference between the partial sums and the value that the series converges to. Let me put it this way. So when we say this series converges, we're saying if you take a partial sum, like let's say from n equals 1 up to n equals capital N minus 1, and you compare that with the value that we are asserting the series converges to, which is this, then this goes to 0 as you take larger and larger capital N, right? So thinking of this as a sequence with capital N as the index, this goes to 0. That's the definition of convergence of this series, right? But if you look at this, this is just this, right? So this is the sum with the first part deleted and just looking at the tail end, which is, we have seen, is mu of a n. So you see mu of an is this, which goes to 0 as n goes to infinity, thanks to the convergence of this series here. Okay, so that finishes the proof of 1 implies 2, and I'm putting a box, I guess, because I said proof of 1 implies 2 here, and that is complete. But we haven't proven the theorem. The theorem is this equivalence of these three. So now we've proven that countably additive implies this condition. Okay, I think the video is running a bit long, so I'm going to split up the proofs of 2 implies 3 and 3 implies 1 into the other videos.